Right now, the question is how much or what's going on in terms of the number of interactions per day that's occurring in this. Now, at this point, it's useful to sort of take an average human, say, and say how many gamma rays per second does the typical human emit? How much radiation comes out of a typical human per second? Does anybody happen to know the answer to that one? How many? It's basically, these are photons, gamma rays that are associated with radioactive decay out of a typical human. Say again?
Not cosmic rays.
Not cosmic rays, no. Just natural radioactivity.
What do you call this?
It is. Start counting.
Yeah.
It's nearly over 1,000 a second. So, right. When I'm doing radiation safety training with the graduate students, one of the things I often do is, I show them the source, and it's great because I, walk over to them and they back away, thinking, and then I absent-mindedly put it in my pocket and keep on talking, and it's great watching the body language. They're all sort of wincing, and eventually they go, Professor Gaitskell, you do know you put that radioactive source in your pocket, don't you? And at that point I say, look, we're better than this, right? You've got to calculate. If you want to be a scientist, you want to be a physicist, it's all about calculation. So let's go and calculate how much radiation I'm getting from absent-mindedly putting this particular radioactive source in my pocket. And we do the damn calculation. We realize I'm getting the same radioactive dose as basically 10 of them that I am from the 10 of them clustered around me.
You don't have any children, do you?
I've already taken care of that bit. No, you're absolutely right. I'll tell you a rather more filthy anecdote about radioactive measurements after, but not in the wider company. But no, absolutely. This is actually, I found out to my horror. My great grandfather was actually involved in the early days of X-ray use in medical physics, and I just happened to come across. I was in a library, the Bodleian in Oxford, and waiting for books to come out of the stack, and I didn't know what to do with myself, so I thought I would go and look up, see whether any relatives had written anything interesting, some steamy pot boiler or something like that. But anyway, it turns out, no, he'd written about bloody X-rays and medical physics. And so I'm trying to figure out, when did he start writing this book, or when did he publish this book? Was I conceived, or rather was my grandfather conceived before or after he developed his fixation with it? Because I'm afraid to say that my genetic material is rather poor grade, because he wrote this damn book before my grandfather was born, which means, given the rather foolhardy ways they had with radiation back then,
so we got the 6 digit on your left hand?
That's the one. Yeah, that's exactly the one. Yeah, no, so anyway, you make lemons with lemonade with what life gives you. Anyway, so the point being is that the sort of activity of a human, which is sort of 10,000 decays per second, represents about a billion decays per day. So this is somewhat contrast to these interaction rates we're expecting from dark matter, which is 1 in this per month, and we're competing with over 1 billion per day in this. So we have to do something about that. And anyway, we've developed a whole series of techniques, one of which is simply to build a lead castle. That's one way. That you actually, it turns out, you can reduce interaction rates from in the unit we tend to use, which is which is events per kilogram per day. So it's events per this guy per day. The typical environmental level is 10 to the 7. We can get that down to 10 to the 2, which is 100, just simply by encasing in lead. But that's still 100, whereas I was talking about 1 per month. So that's what we're 100 times 30. We're still 3,000 adrift. So what we've had to do is we've developed various techniques in order to further reduce background. One of the most interesting of which is to differentiate between nuclear recoils, which is energy deposited by hitting a nucleus, which is what we think dark matter does, and electron recoils. So let me now show you the sort of, if you like, the incarnation of a detector that does this. Well, actually, I can really. This is actually an incarnation of humans' inventiveness. This is just a small set of all the damn detectors that are either running right now or will be built shortly, looking for this damn dark matter. And actually, I realise this is only about a third of them. It never strikes me. We're terribly imaginative. Anyway, this is the one I happen to be the leader of, the Lux LUX experiment. Frankly, photogenically, I think we're losing the battle. We need to get some brighter colours in here or something. But no, these are all what we might lose photographically. We gain on pure bloody brilliance. Anyway,
Of course, right.
so let me show you how one of these detectors works. And it's a target of liquid xenon. It's about 1/3 of a ton of it. It's big. Actually, it's not that big. You know, it was just sort of maybe 60 centimeters, 70 centimeters across. The whole canister is about 2 meters. The actual target is only about this big, 60 centimeters sort of thing. So it's kind of this cylinder here, 60 centimeters.
Where did you get that much of that?
Say again?
Where did you get that much?
Out of the atmosphere, would you believe?
You don't have to go down warmer.
For xenon, I wish they did actually. It costs. When we bought it, I mean, honestly, I back in the 80s, I used to be an investment banker, and not something you admit to in polite company, I think.
Currently, it's rather out of fashion. Yes,
it's extremely out of fashion. But anyway, when we were putting this experiment planning this experiment, we phoned up people and said, "Oh, we need to buy 350, 1/3 of a ton of xenon, please." And they said, "Oh, that'll be $400,000. Thank you very much." And then they said, "Well, it will be if you buy it today. But if you wait 2 months, it's probably going to be $600,000. And if you wait another 2 months beyond that, we reckon it'll probably cost you about $1.5 million." We said, "Oh, that's going to be a problem." So we actually rushed around and got enough money together to buy it there and then. And yes, they were absolutely right. In fact, the price of 1/3 of a ton of xenon is now some $4 million. It's a rather inelastic, I believe, is the phrase for those of you who are economists. It turns out that there are some rather entertaining, you can get high on this stuff. So our medical friends, needless to say, are always big on anything that makes them get high. They're using it as an anesthetic. If you're going to have a heart operation, xenon is a great anesthetic because it stresses your body rather less than a conventional general anesthetic. It also, in your light bulbs, in your, the better, the cars with the halogen light bulbs, those have xenon in them. Anyway, sorry, I'm digressing. So 1/3 of a ton of xenon. I should think. So the way that the detector works is the following. So this is 1/3 of a ton, and these arrays here are photodetectors, which means they simply pick up photons. They pick up light. Xenon has this interesting property that if you kick it very slightly, either by a particle interaction, scattering off an electron, or off a nucleus, and I'm going to show you one scattering off a nucleus, which is actually generated by a WIMP coming in, it lets off a small amount of light, and we pick that up with this photodetector array. But a second thing happens, which is ionization. A small amount of ionization is generated. They're electrons, and those electrons will drift because we apply a field. These things here are actually grids, which allow us to apply a field. And those electrons are going to drift up to the top, and when they hit the top of the liquid, there will be a second flash of light, because it turns out the physics of the electrons moving into the gas, which is what the phase is here, also generates light. Now this is what's known as a time projection chamber, and I hope in this animation I can give you a sense of how that works. So here comes the WIMP, bounces off the xenon, flash of light, bang, gets picked up. It's brighter down here because light tends to reflect off the underside of the liquid surface and come back down here. These are the electrons which are moving off. This is taking place on sort of 100 millionths of a second time scale. When they hit the gas, they light up again, and you get this rather large but very localized hit pattern up there. And this, in the jargon, we refer to this as the primary and secondary light. Now what's great about this signal is that it just tells you everything you want to know. This initial interaction, the amount of light that comes off tells you how much energy it was deposited. The more light you get, the more energy. The initial flash of light tells you when this first interaction is. The delay between that initial flash of light and the second flash of light when the electrons hit the top tells you how far the electrons had to drift in the z direction. They're going a few millimeters every microsecond.
Does anything happen to the nucleus here? Is there a change in the nucleus?
It just goes off and sulks. It's ionized for a while, it wanders around, and then it just picks up a few electrons and so nothing happens to the nucleus. It's what's known in the jargon as an elastic recoil. So all that happened is the xenon itself, nucleus got displaced from whatever